So that's going to lead us to optimizations. So if I'm going to make this smaller, good. Okay, so optimizations, there's a few reasons why. One is literally just to make it faster, but also there's a few reasons why we actually want to make these optimizations work. So the first thing basically, like I said, like one is just to make it run faster. Because if you run a faster model, it means that you can actually use higher complexity to find these parts. If it takes way too long for your model to actually run, then it's no good, right? Even though if it would be great, theoretically, if you could run the whole thing through over 100 years or, you know, the age of the universe, it's like, well, that's great, but that's not what's going to happen here. Like we need to actually get these things. We also wanted to run better. We actually wanted to find the local, like the global minimum of the cost function. We want it to actually find a good answer. We don't want it to be stuck on like the easy answer, essentially. Like essentially the way I think of this is like if your test is really easy and like all the answers are A, at first, you know, you might say, oh, you're trying to figure out like, you know, like I'll say like A, B, C, right? It's something different, like, you know, fill in the blanks. And at first, maybe you're like, okay, like I'm going to really study for this test, you know, and you don't do that well. But then you start noticing, hey, if I just choose A, that's always the answer. Then you stop studying for the test, basically. You just start picking A. And it's a good enough, you know, strategy for you to actually pass the test. We don't want something like that. We actually want to find a good answer regardless of how the test is written. That's kind of what I'm getting at. But so I will point to a couple resources for optimization. One is actually Keras' optimizers, which I don't have to learn actually points to this, but if you're using Keras, there's a whole like basically like ways of including optimizations. We did SGD, which is stochastic gradient descent, which we'll talk about in a second. There's a few ones that basically the curriculum talks about. There's a whole bunch of different optimizations, and these are all ones you can basically add into doing your what's it called, creating your neural network, your multiple layer perceptron network, right? Basically, these are different ways we can do this, and they have advantages and stuff like this. And so I'm not going to go through all of them because there's a whole lot of stuff. But in this blog post right here, which is really great, he doesn't just talk about just optimizer. He talks about a whole bunch of things that we're going to talk about today, including momentum. But there's basically other optimizations like AdaGrad, where's Eta Delta, where's Atom, RMS prop, Atom. They're basically, he goes through a lot of detail, like, you know, mathematically, like what these things are doing. So this would be a great resource to check out. Okay, but just know there's just a bunch of stuff you can do, and there's always new stuff kind of being researched and applied and seeing what works well for an optimization. Okay, so that's the general kind of idea of what optimizations are. So one thing we want to talk about is the vanishing gradient problem, which I think I talked about last time too, but we'll kind of talk about this. Is that, why is this like this? Oh, there we go. Okay, so the vanishing gradient problem, like I mentioned last time, basically it's when your gradients are so small that basically they don't proceed any further. So you can imagine this on like your cost function. If your cost function looks like, this is 2D, but like you imagine multiple dimensional. If that your cost function is really flat, like this, okay? The problem is that, let's say this is a better gradient and it lands to right here, right? Well, it might get stuck here, or the fact that this is like a really flat derivative, okay? The problem is that it's, because it's adjusting the weights based off the derivative, it's just going to basically just never get to over here because basically it's really flat. This also can happen when like we have like a local minimum, that's our local minimum, and then there's like, we have a little flat area and then like a global minimum, which this is a much better spot. If we don't do some optimizations, including other stuff, we can get stuck here. And one of the issues can be is that if the gradient's just too small, if it's too flat of an area, essentially its gradient's gonna be too small, so it's not gonna take very big steps, so it's never gonna go over this hump. So there's a few things we can do. One, like I mentioned last time, is with activation functions, is that we can actually just change the different activation function. For example, we talked about ReLU, allowing you to basically have a higher derivative in that way. So we actually go closer to something. Sigmoid tends to be not very great at this. This is why sigmoids tend to be considered more old school, is that it doesn't converge as quickly. And so it can find local minimums and never find the actual global minimum or a better minimum because it gets stuck basically because of its small gradient. So basically we can change our activation function to have higher gradients. So we talked about this last time, so I won't repeat a whole bunch of this. Okay. One other thing we can do is random starts. So random starts basically allow us to avoid local minimums. You can think of it as basically just initializing our weights in different parts. And when we say initialize our weights, the way I kind of imagine this is that we're literally putting our person, like our little person who's walking down the hill, in different parts. So let's say our functions, and let's say this blue guy is like where we initialize the weights. So we initialize the weights right here, just randomly, right? Those are just random weights, and on the cost function, he ends up being right here. Another time we basically initialize maybe like right here with the random weights. Maybe we get lucky and we kind of initialize in this global minimum right here. Okay, and the idea here is if we would randomly initialize the weights, that way we kind of have as many times as we can. Maybe if we initialize right here, this person instead of going right will just by chance go right here, and that will find this minimum here. But maybe these two guys, for example, will actually find this global minimum right here. Okay, and we can actually, when we do that, it's like, okay, we can actually see what was the better model, and better model is the smaller cost. Okay, the smaller the cost can be, the better that algorithm was, or sorry, that model was. Okay, so again, this is kind of like a really simple way to do this. One disadvantage, as you might guess, is that you have to run the model multiple times. You have to initialize, readjust the weights, initialize, readjust the weights, and do it over and over and over again. Which again, you know, you trade time in for getting a better model, essentially. But the idea here is that you would actually just run this multiple times, the same model structure, and just reinitialize the weights every time. This is one of the reasons why we don't like usually use the weights just set to 0, like, because then it's basically you don't have any change. This is why we initialize stuff. You also, kind of going off of this is not a random start. We can actually specifically choose the weights to be something. And when I say specifically choose the weights, it's like, I don't know what the weight should be, right? I don't know what the numbers should actually be. What I usually mean is that we might have, later on we'll see transfer learning for convolutional neural networks. Basically, we can set up the weights to be, use these weights and start from here. That's a possibility too. But for random starts, we essentially just initialize different parts of, or initialize the weights to be different things, the different biases, and that will basically put us on the weight, the cost function at different points before we start gradient descent. Okay. Any questions on this? Okay, cool. This is a pretty straightforward, I think, solution that makes a lot of sense. It's also really useful. It just takes more time though. The next part is momentum, which I think I mentioned a little bit. I think it's from our last our implementation on Keras, we actually used momentum. And so momentum, the concept of it, hopefully you can kind of hopefully hear it from the name, is that essentially what we're doing is we have some kind of like hill, but we have like this part right here, like this is the actual minimum. And the problem is our guy, right? We start right here and we end up falling into this hole, right? And once we end this hole, we end up taking 2 small steps, or we just kind of oscillate back and forth within this hole, and we never get out of it. So the one way we can kind of imagine is like we can basically include momentum in here. So if I do something like, let's say we have our different size of our changes in our direction of where we go. Okay, what we can do basically, we can essentially average up these steps and say, well, okay, like where were you going originally before you found this very small, basically this very small step. So you can basically add up these parts together. It's like, well, okay, this averages over to going off to the right over here. And that hopefully will give it a little boost to make it, help it go over this hill and explore this area. If there isn't an area to explore, it would end up going back here in the long end. So to kind of formulate this, it basically will power over this hill. It will dampen oscillation. So like I said, if you're in this, this minimum, you tend to like go back and forth, back and forth, back and forth within this minimum, because basically you're going hopping back and forth, back and forth. Basically it dampens it down smaller and smaller, so you stay within there and you don't have to like see your model going up and down, up and down, up and down. It kind of allows you to go quicker into that hill. So there's a couple ways you can kind of think about this. One way I like to think about it is that basically you have this beta, this decay factor right here, okay? And basically is that every step, this S represents a step, okay? And so you can think of like this, this step basically, it's like the last step basically is equal to its previous step times beta plus beta squared times its previous step. And so that way it still is including the old stuff, but the stuff further in the past, its steps previously count less and less and less and less. And you can basically think of it like only counting, like usually we maybe only count like 3 or 5 different steps at most, saying average this all out. Another way you can think about basically is this is actually what the curriculum shows right here, is that you can think of it like in these kind of terms, is that essentially you're like, okay, you're taking the original step, this should be really Sn plus 1, sorry. But this Sn plus 1 is equal to basically its previous step plus the previous one before that, this difference times its beta. So basically it's like what change did you have times the beta, so it adds a little extra bit to whatever you needed it to do. So this allows you to kind of incorporate some history of where you were going before, and that basically allows you to have momentum. And basically you're trying to still go in that direction of where you were previously. And this hopefully can get you over the hill or can help dampen your descent into the local or the minimum right here. Okay, cool. Any questions, Sazan? Cool, all right, awesome. All right, and this is like, again, this is the mathematics, but in reality, you probably would use like something like Keras where you would literally just take momentum equals and give it a factor for the beta. Usually about 0.9 tends to be what we use for momentum. Okay, so those are a few things to address the vanishing gradient problem. Note that some of these things, for example, like some of these things can also help speed up parts. Like for example, momentum can actually help speed up finding minimums and stuff like this. But these directly affect the vanishing gradient. So another reason why we optimize is just speeding it up. So one way we can do this is normalization. And normalization, you can think of back like, I think really far ago, like module 1, when we talked about standardization, scaling, let's see here. What else did we do? Min-max scaling. Min-max scaling is pretty typical. We basically say, all right, let's get the minimum value and the maximum value and set those equal to 0 and 1, and we squish all the values within 0 and 1. And this actually can help us do faster training, because one of the reasons why is basically no one feature dominates over each other. So basically, if you think of all the features are between 0 and 1, no one feature actually dominates really well. And remember, the whole reason why we're able to do this stuff is through gradient descent, which is reliant on not just the gradient, but also what the feature value was to begin with. So if the feature value is very, very large, it'll take a much bigger step, and that's something you might not want to do. So it actually turns out that normalizing can actually make it speed your training, and it'll also mean that that you're more likely to actually hit the minimum too. So this is kind of like a 2-in-1 kind of deal. So normalization is pretty typical. You would normalize your values before you do your actual neural network. Okay. And then we have stochastic gradient descent, or SGD, as you saw like in Keras. Stochastic, you can think of stochastic just being like random. And really what it means is that instead of taking like a long time to actually like go through the whole process of the data set. So when we talk about like our feed forward thing, we can basically provide the whole data set through the feed forward, basically process all that data through, okay, on the feed forward of the network, stop here, compare the losses, back propagate it for adjust all the weights from those parts. And the back propagation actually doesn't matter going backwards, but it's the feed forward that can take a long time. So one thing we can do is basically say, well, okay, what if instead we just take random batches? And the idea here, I think we kind of talked about this, is basically you take a random part of the data set, instead of the whole training set, you just take a random part and you feed it through the network. You basically feed it through, and that way, instead of having, let's say 500,000 data points, you only have 1,000. It's like, that's so much easier for the what's it called? The network to actually push it through, feed forward, and it won't actually like get the best answer because you're only using 1,000 points. But it means that you can go through a lot quicker, and you can basically make, let's just make up a number. You can go through like 50 times more epochs in with these batches versus going through one whole thing with the whole data set for training. So this kind of allows you to have some speed to it. And the best kind of comparison I've heard about this is like you're taking quick drunken steps. So if you imagine, like, if I have this hill, that's where I wish I was a little bit better drawer, but I have this big hill, for example, and I want to find the minimum right here. Or, you know, actually I'm going to redraw that a little bit better. So let's say I have like this steep hill like this. Okay, the problem is that if I had something like, you know, the regular efficient, or not efficient, the whole data set, this like person going down the hill would basically equivalently taking very small steps, very careful steps. It would basically think every time, go, okay, It goes to the data set. It's basically feed forward this thing. He's like, okay, which direction should I go? All right, I'm going to go this direction. And then it takes that direction downward. And because there's so many data points, it might actually take smaller steps too. Versus if I had something like our quick drunk person, which sounds kind of like it shouldn't be good. But if our little quick drunk person, he's like, okay, let me just use the quick data right now. All right, we're going to go in this direction. Okay, we're actually going to go back up a little bit. Okay, we're going to go back down a little bit. Okay, we're going to go back up again. We're going to go down. Okay, and what happens is like, okay, we're going to go up. Oh, we're going to go up. But basically, even though he's taking more steps, he's doing it very, very quickly, where eventually he actually will land here much faster than we would if we had taken all the data sets going through, because you have to basically be thinking a lot. So this basically, this little gradient descenter basically is thinking very, very quickly to go forward faster and faster and faster. So the way you can kind of think of these steps, actually implementing it, is basically you think like, okay, we get a random set, which is like our batch. We feed the batch through the model. We see how bad our model was from that batch. Then we basically backpropagate and adjust all the weights, and then we just repeat again, okay, over and over again. And this is why it's actually so nice. It's because this is very fast compared to using the whole data. So if we basically do these batches, very relatively small batches, we can go through it very quickly. And the idea here is that because it's stochastic, meaning random, right, is that if we do this over and over again, if we do this enough times, eventually we'll see all the data. And there's a few ways you can do it. You can either make things like mini batches where you split them up specifically and say, all right, I'm using for the first epoch this set of data, next time I'm using this set of data, and I'm going to use this set of data, versus you just randomly pick from the hat and then throw it back in, pick from the hat, throw it back in. Both of those ways are valid ways. They tend to be relatively similar performance. But the idea here is stochastic, is that we can basically quickly, drunkenly go down the hill versus very carefully going down the hill. We take more steps, but the steps take less time to actually do. And our steps aren't really epochs. Okay, cool. Any questions? Okay, cool. And again, just to reemphasize, since I already said epochs, this right here, this whole thing is one epoch. Yeah, I'm writing. Basically, that whole thing's an epoch. Okay, so our last one, which I think, okay, I was gonna say, I don't think the Learn curriculum does actually talk about this, but it does. Learning rate decay. So learning rate decay, basically, like the problem is that with learning rate, basically, if we have a very high learning rate, alpha, right, we move really, really quickly, or we move very, very quickly down the mountain. Basically, our alpha is adjusting how far we should step. But if we make very, very large steps, we might step over our local minimum and keep going, or we'll oscillate for a very, very long time. So that's not ideal. A low learning rate, it means that we have a very small alpha, which means we move very slowly and we might not ever get there. So like it might take way too long for us to actually traverse down into the minimum that we're searching for. So there's advantages and disadvantages for each. So basically learning rate decay says, all right, well, what if we just do both of them? What if we just say, okay, we'll do a high learning rate when we're first trying to find our model, or find our minimum. And then as we progress forward and we're getting closer to that minimum, we'll go ahead and use a small alpha. So there's a few ways you can approach this. One, basically, is just saying as you get more epochs, your alpha will decrease. So one way we can do this, like one typical way we can quickly do this is something like you say alpha times like, let's say like 0.9 to the power of number of epochs. So the idea here is that as the number of epochs increase, for example, let's do like 99. But like as the number of epochs increase, this value gets smaller and smaller and smaller, which effectively makes this effective alpha smaller and smaller and smaller. So basically we would reset alpha to this value. So alpha is going to be equal to this smaller and smaller and smaller and smaller, right? That's one way. There's a bunch of other ways you can do it too. One such way that can be done in research, though it might not be super efficient, I actually don't know if anyone's actually implemented this well. But one thing is like if you actually see your gradients very small, maybe you actually decrease your alpha even more to make it smaller steps. Basically the idea is like as you're getting into more of a a flat area, you're probably bottoming out. So you can possibly take smaller and smaller steps that way. Both of these things, basically, the reason why we use the number of epochs to decrease alpha is the idea is that as we increase the number of epochs, we're probably getting closer and closer to the actual minimum. So that's kind of the idea here too. Note, of course, you can probably think of scenarios where this would not work very well, which we can use our other optimizations to kind of circumvent us falling into that trap of a local minimum versus a global minimum. Okay, cool. So that is it right there. Do you have any questions aside, whether it's learning rate decay or anything else that we talked about?
No, I think for the most part I got it.
Okay, cool. Yeah, and again, these are just all different things basically to optimize like your neural network. And basically it comes down to the fact that if you just feed the data directly into a neural network, it probably won't work. And it's because of all these different reasons. And so these are things to kind of consider as you're kind of adjusting through. But soon enough, basically you'll do it more or less automatically. And again, using something like Keras, like we saw kind of similar right here, is that we don't have to, where is it? Oh, here it is. Like, for example, some of these stuff, for example, we're already automatically kind of putting them in here, creating an optimizer. And we can see all these parts in these different hyperparameters. One thing I didn't mention is that all of these hyperparameters, which is like all these different solutions that we came up with, even some of the parts of overfitting, for example, I think we talked about like lambda for regularization. Those parts, it's not super clear exactly what the value should be. You would basically do something like a grid search. And you can do a grid search on all these hyperparameters and basically run multiple models with tweaking the different hyperparameters that will hopefully help optimize even better. And that can help you through. And that's what can give neural networks a long time, just because you're basically running multiple models and making sure which one's the best one, essentially. So, but you can usually start off at a good spot and say, okay, well, I know these optimizers and these processes will actually do a good job of getting a good neural network model. Okay, cool. So I'll go ahead and stop the recording then.